Hello, here we are again. We are trying to do another rate of reaction question. Now, this question again, pretty similar to the previous one, based on the same experiment. Yeah, have a look at that. It is based on the same experiment. Question 4. What is the experiment? No, I was meant to say the same chemical reaction. In this chemical reaction, as I said, as we discussed earlier, hydrochloric acid reacting with magnesium to form magnesium chloride and hydrogen. Then what are we trying to do? This time, what we have got different conditions. Different condition in A flask A, concentration of acid is 0.1 F, volume of hydrogen we have 50, temperature is 20. B, we have changed the what? We have changed the concentration there. We are collecting the same volume, temperature is constant. So according to this, you see that they change the control variables. No, independent variables change. Yeah, so sometimes the variables are not controlled. In some cases, it's everywhere. Anyway, unless in flask C, you have hydrochloric acid, which is 0.2 m, volume 50, different temperature. Okay, so the conditions are not consistent here. But let's see what we can do about this, okay? All right. Now, here it says in each experiment initiated by adding 0.08 grams of clean magnesium ribbon. Magnesium ribbon it's a solid, okay? It's not a powder. So when you get magnesium, it comes as ribbon, it's a solid. So the surface area, what really matters. So rate determining factor when you use a solid is the what? Solid is the surface area. Anyhow, the volume of the hydrogen gas produced was measured SLC, the result flask A. Okay, now they have given us the results only for the flask A. So let's focus on flask A, which has got the concentration of 0.1 m of hydrochloric acid. We are trying to collect 50 milliliters collected in 20 degrees of Celsius. Now, question is asking you, calculate the amount of moles of hydronium ions. Now, you might be very confused with the word hydronium ion. Hydronium ions are H plus, right? Uh, now, so it is pretty much H plus is equal to the hydronium ion. So if you can find out the amount of HCl which is going to be left over, that will equal to the amount of H pluses, number of moles of H pluses. So that will also same as that will also be equal to that will also what I was saying, I'm struggling to come up with a sentence, I'm sorry. So when if you can find out the number of leftover moles of hydrochloric acid, it is going to be equal to the H plus ion concentration. If H plus number of moles of H plus ions, then it will also be equal to the number of moles of H3O, or which is the hydronium. Okay. All right, that's what I was meant to say. Now, in order to do that, what do you have to do? Okay. By the way, how is the day going? Huh? Too many sacks coming up. That's the life of a student. Okay. All right. Now, in this case, what you need to do, we need to find out the flask. No, we need to find out the number of moles of hydrochloric acid, which is going to be left over in flask A. Because our limiting is going to be the magnesium. So we have to assume that all that magnesium is going to be used. So firstly, find out the number of moles of magnesium, because they say it has to be the leftover. Why? Because they say calculate the amount of moles of hydronium ion present. So magnesium should be the limiting. So find out the number of moles of magnesium used, right? Used, which is the limiting. 0.080 divided by 24.3. That will give you, that's the number of moles of magnesium used. Then what is the number of moles of hydrogen HCl reacted? Reacted is 0.080 divided by 24.3, and you times by 2, because why? Why do you times by 2? Ratio is 1 to 2. Then that will give you, you can leave that number of moles. Okay. Then you know the number of moles of HCl use. It is what? Concentration given to you. What is the volume of the HCl? Flask is shown below. Volume of the HCl added. Let me check the volume of the flask. What is the volume of the flask? Flask table 1. I could not find the volume of the flask here. Hydrogen gas reacted. What is going on here? Huh? So volume is the flask is 50. Yes, it says 50 milliliters. What are you talking about? So, yeah. So then number of moles of HCl initial. Initial is what? 0. Concentration is 0.15 times 50 times 10 to the power minus 3. Yeah? How did you get that? N equals CV. N equals CV. So then you can find out the therefore number of moles of HCl remaining, which is going to be our leftover or remaining is, this is not good, leftover, which is what? The difference between those two, right? So this is the initial, this is the what? This is the reacted. The difference is the number of moles of HCl left over. If you put those numbers into a calculator, you should get 9.2 times 10 to the power minus 4 moles. Okay, that's the number of moles of HCl ions. Now the question is asking you hydronium. Look, when HCl reacts with water, you are going to produce H3O plus and Cl minus. There's no double arrow there. It's a single arrow. That's a strong acid. So that is going to go into completion. Therefore, if you had 9.2 10 to the power minus 3 moles of HCl left over, you will end up getting same number of moles of H3O plus as well. Is that clear? So the answer is number of moles of H3O plus is also going to be 9.2 times 10 to the power minus 3 moles. Okay? How did you go with that question? Bit of calculation, stoichiometry, right? Not so much a writing question or explanation question, but you have to use a couple of important stoichiometric concepts. What's that? Limiting reagent, yeah, and this, because our limiting was the magnesium. How did you know it was a magnesium? Because they said hydrochloric acid is going to be left over. Therefore, we had to assume that magnesium is the limiting reactant. In other words, we had to assume that all the magnesium is going to be reactive. Okay? All right, that part is done. Now, if you look at the next question, it's an interesting question. What? You just need to use your knowledge in rate of reaction. Right? Okay, let's have a look at this question here. Part C. To investigate the effect of surface area of the solid reactant on the rate of the same reaction, a further 3 flasks were set up, okay, blah, 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 conducted as described. So what they are saying now, this time, they are trying to investigate how surface area affects the rate of reaction. You know that surface area, when the surface area increases, if the surface area increases, the rate of reaction will increase. Okay. Now the question asking you which flask in table 2 provide the most informative results on the effect of, is that the question? No. Sorry, I should have gone back. Sorry about that. B. Okay, on the above axis, sketch the result for flask B. Flask B, what is flask B? What's the difference between flask A and B? B will have the higher concentration of HCl. Rest of the conditions are the same. Now, should you be getting higher volume of hydrogen? No, because our limiting is the magnesium. So you are going to get the same same amount of hydrogen, because we are not changing the amount of magnesium. But since the concentration is higher in B than A, you are going to get the same amount in a faster rate. Faster rate. So I would do, this is the faster rate. So the gradient is higher gradient. So this is B, yeah? Is that clear to you? All right, that's done. On the above, flask C. Flask C. What is the difference between B and C? Oh, higher temperature, same concentration of the hydrochloric acid, same volume, but the temperature is high. So the C has to be much higher rate. So that is C. The gradient is highest in C. That's simple. All right. Yeah. How did you go? Now rate is rate of a reaction is the gradient of a reaction. Steeper the gradient, higher the rate. So in this question, we are going to get the same amount of hydrogen because we are not changing the amount of the limiting. However, though even though the same amount, which is 50 milliliters, you get that 50 milliliters in different rates. In C, we'll take the shortest amount of time because highest rate can be found in C because temperature is high. Yeah. Then B only reason is the concentration is high. All right. Okay, let's go into the next question. Okay, in the next question, what are we doing? We are trying to change what? We are trying to investigate the effect of surface area. So if you are trying to investigate the effect of surface area, you need to keep all the other condition controlled. Only thing you should change is the surface area. How would you change the surface area? Look, if you had used a magnesium ribbon, this time you can use magnesium powder. Ribbon is a solid, powder is a solid. Powder also a solid, but it will have higher surface area. All right, so in this case, the question is asking you which flask in table 2 provide the most informative results on the effect of surface area on the rate of reaction when analyzed in conjunction with the table 1. So you need to find you need to find a flask in table 1 which should have the same conditions as B, we should have the same condition as this table, but only change, or the only dependent or the independent variable should be the ribbon becomes. So this time you should use a powder, because in table A is based on magnesium as a ribbon, which is a solid, but it's a ribbon, not a powder. Now in this case, if you are comparing the previous conditions into magnesium powder, because you are trying to investigate how surface area changes, so only thing you had to do, you had to keep the condition same. Only condition you should change is a powder surface area. So they are asking you which flask in table 2. All right, so then what you need to do, you need to find two flasks, one flask in table 1 and one flask in table 2, which should have the same condition except the surface area. So one should have a ribbon, big particles, which is the big particles, the other one should have powder. So the answer is, if you compare those, look, compare this D and E. E from here, yeah, D from here. They all have the same conditions, same concentration, same volume, same temperature. Look, same concentration here, same volume, same temperature, but instead of magnesium ribbon, you have magnesium powder. So D and E should be the answer. D and E should be the flask that you should be comparing. So from table 2, you need to choose which flask? Table 2, you need to choose the tape flask E. Then after that, you have to say, in order to obtain valid results, uh, in order to obtain valid results, in order to obtain valid results, right? Both the flask in with should have same condition except the surface area of the magnesium, right? So that covers magnesium. So that covers the answer for that question. So 2 marks for this and this, right? Yeah. Going back to this question again, what did you have to pretty much do? You had to choose 2 flasks. In both of those flasks, all the conditions should be the same except the surface area of the magnesium. So you need to do bit of searching, right? Okay, now we are going to do the last part here. So the last part, the question is asking, what does the question say? The number of successful collisions between reactant particle is less than 1% of the total number of collisions. 2 reasons. So what are the 2 reasons? I mean, it's a sort of a good question. Why it is a good question? They are asking you 2 reasons. Normally you will end up giving a 1 reason. I mean, you will end up getting a 1 mark. Most of you are going to say what you will be saying, in order for successful collision to occur, particles should have the correct orientation and the energy to overcome the activation energy barrier. Okay, those are the 2 reasons that you are going to mention, but in this case you will only get 1 mark, right? Why you normally say that, don't you? Say particle must collide with the correct orientation, particle must possess the energy higher than the activation energy, so that the existing bonds of the reactant are broken. I mean, when the particles collide with correct orientation and the right amount of energy, that is only when the existing bonds in the reactants are going to be broken. I mean, if you say that, unfortunately, you are only going to get what? You are only going to get 1 mark. So, okay, I'll tell you exactly what you need to write. You have to write to produce successful collision. To produce successful collision. To produce successful. Okay. Successful collisions. Successful collisions. To produce successful collisions, right? Okay. The reactant particle must collide in the correct orientation. The reactant particles must collide in correct orientation and correct orientation and what? And energy, with energy to overcome the activation energy. Okay, so that's 1 mark. Then you have to say the another mark is for the reactant have enormous range of energies. Reactants have ranges of energies. Don't have to say enormous. Range of energies. With only, now we have to refer to that. Look, we have in the previous answer we said what the condition that needs to be satisfied, but then you have to say why it's only 1%. Then that's what we are explaining in the second point. The reactants have range of energy with only a small fraction having the energy required. What we are saying is when it comes to what we are trying to say is when it comes to particles, the particles possess various ranges of energy. In other words, not all the particles will have the same amount of energy. I mean, we don't tend to spend too much time on Maxwell-Boltzmann distribution curve, if you can remember. Maxwell-Boltzmann distribution curve. So particles, that will show you the amount of energies a particle having. So there is a range of energy. So maximum Boltzmann graph, it goes going like that. So it will show you that the range of energies, not all the particles have the same amount of energy, even though they are in the same temperature. Okay. So that is what we are trying to say, having energy required. Yeah, so that is the that should be the answer. Okay, if you write the answer like that, I think you are going to get both marks here. Oh, we could mention something else as well. And then these particles, not just the energy, must collide. I mean, you have to mention this as well. You have to say, and it's only small fraction of the particle will have energy higher than the activation energy. At the same time, those particles must collide in the correct orientation. So that the bonds are broken and new bonds are formed. Is that clear? Yeah. I really want you to have a look at this question here because especially, I mean, this question, not so much calculation, but there are, I mean, if you look at the last part of this question where you had to get 2 marks, you have to write not only the fact that not only mention the condition that need to be satisfied, you have to specifically say if you have a mixture of particles, not all the particles are going to have the same amount of energy. They have various range of energy, right? Only small portion of the particle have energy higher than the activation energy. Among those particles, they also have to, when it comes to those particles, they also have to they also have to collide in the correct orientation so that the existing bonds in the reactants are broken, new bonds are formed. All right? Not a bad question. All right, I'll talk to you soon with another question. Bye-bye.